Hi, this is Mr. Flint, and we're going to be doing some projectile motion problems this morning. Let's look at our first problem. It says a potato cannon fires a potato so that it has an initial velocity with components of 90 meters per second forward and 30 meters per second up. Or we could say 90 meters per second horizontally and 30 meters per second vertically. Part A asks, how much time passes before the potato strikes the ground? So let's list out some information. This is our givens. We know that the initial velocity in the horizontal direction is 90 meters per second, and the initial velocity vertically is 30 meters per second. We also know our acceleration, and that is 10 meters per second squared. Alright, the unknown that we don't know is time, so we've got to figure out time for this. So let's find an equation here. And the equation that we're going to want to use is, we're going to be using change in velocity with acceleration in time. So we know that acceleration is change in velocity over time. So then we can rearrange this to solve for time, and we get time is equal to change in velocity over the acceleration of the object. Alright, so then we need to figure out a change in velocity of the object. Now, we only are going to be dealing with the vertical component of this. This ends up being a free fall problem if we do that. So we're going to look at this potato being launched, and it's going to go and get launched from the ground and shoot up, okay, and go to some height, and then it's going to fall directly back down on itself. Come right back down to the ground, okay? And we know that it's launched at 30 meters per second vertically. And we know the acceleration is 10 meters per second squared. Now, we need to make sure to know that this is really a negative 10 meters per second squared. So we're going to plug in a negative number to the acceleration here. So let's go ahead and plug in our numbers, change in velocity. Well, if it starts at 30 meters per second and comes back down to the same place, to the same position, what will its velocity be at that position coming back down? Well, it would be negative 30 meters per second. So your change really is going to be twice that initial vertical velocity. It would end up like this. Change in velocity would be your final velocity minus your initial velocity, in which case we would get change in velocity is equal to negative 30 meters per second minus 30 meters per second, or we would end up with a change in velocity of negative 60 meters per second. We just need to know twice that value. Alright, so twice the original value would be our change in velocity. So when we do this, time is equal to our change in velocity, which is negative 60 meters per second, where it's accelerating at negative 10 meters per second squared. We end up with an answer of 6 seconds here. It's in the air for 6 seconds on this one. Alright, so now let's look at B. What horizontal distance does the potato travel before striking the ground? Well, we know that it's in the air for 6 seconds now, so when we re-list out our givens, we can put time as one of our givens. So let's do our givens again, and we've got the initial horizontal velocity of 90 meters per second, the vertical velocity of 30 meters per second. Sorry about that line, pen messed up there. And then we get time. We solve for it, and it is 6 seconds. Alright, so our unknown this time is how far it goes horizontally. We don't know that. So let's find an equation that will help us solve for this, and we can just use your normal formula for displacement, and we can go velocity. We'll do the initial horizontal velocity because we know that remains constant, multiplied by the time. So when we substitute and solve for this thing, we are going to put in the initial horizontal velocity, which we know is 90 meters per second, and we just solve for the time, which we said was 6 seconds. So when we come up with our answer here, we should get 540 meters. So let me write that down. Okay. So there's question number 1. Now let's go on to question number 2. Okay, question number 2 says a bullet is fired with an initial velocity of 300 meters per second at an angle of 37 degrees from the level ground. Determine the amount of time the bullet spends in the air. All right, so it's fired from the ground, comes back to the ground. So we've got a bullet that starts at the ground level, goes up, comes back down, hits the ground again, comes back to ground level. So we're just going to go ground to ground here. And that's what it looks like in terms of a picture. Let's list out our givens. Our givens here are an initial velocity of 300 meters per second. Okay, so it's going to be launched at 300 meters per second at an angle of 37 degrees. And so there's our Greek letter theta, representing angle. Instead of writing out angle, we just write theta, means angle. Okay, so this is launched at 300 meters per second at an angle of 37 degrees. All right, now part A asks us to determine the amount of time the bullet spends in the air. Or not part A, just the whole question. So in order to do that, we need to know the vertical velocity. We need to know how long it takes for it to get up to its maximum height here. How long it takes to do that, and how long it takes to come back down. Well, it's very similar to the problem that we just did, except we don't know the initial velocity in the vertical direction. Okay, and we also don't know time, and we need to know these two things in order to solve for time. Well, how do we get initial velocity in the vertical direction? Well, we need to use our definitions of sine, cosine, and tangent. So we've got this bullet being launched at 300 meters per second, and it's along the ground. So let's do the ground level here, and we've got 37 degrees for the angle that's being launched at. So this is going to actually be broken out into two components, a horizontal component and a vertical component. Well, right now we don't care about the horizontal, we only care about the vertical component of the velocity. So here's our initial velocity, and we want to know what the vertical component of that is. Well, that's opposite the side, that's opposite the, this side is opposite the angle. So when we do that, we know the hypotenuse, and the hypotenuse is 300, and we want to figure out the side opposite, and we know the angle. So we can use the sine function, and it says sine of the angle, that's the s part, is equal to the opposite over the hypotenuse. So we can then plug in things that we can plug in variables. We know the initial velocity is the hypotenuse, and the initial velocity in the y direction is the opposite. So we're going to use that formula. Sorry again about the line appearing there. Little pad's kind of having some difficulties today. Alright, so let's rearrange this to solve for initial velocity. So initial velocity in the vertical direction is going to be equal to the initial velocity times the sine of the angle, and we've seen this before. This is an important formula for you to have memorized right here. Now let's plug in some numbers to solve for the vertical velocity, the initial vertical velocity. So we'll take the initial velocity, which was given to us as 300 meters per second, multiply that by the sine of 37 degrees. Okay? And what is the sine of 37 degrees? Well, you've got this little table here, and we can find 37 degrees, and the sine of 37 degrees is actually 3/5. Okay, it's actually 3/5. So we can take 300 and multiply it by 3/5 here, and that will give us our answer. So not our complete answer, but it'll answer part of this that we need to multiply by 3/5. So when we do that, that's like 300 times 3, which is 900, and divide it by 5. So that's equal to 180 meters per second. That gives us the vertical velocity in the the initial velocity in the vertical direction. All right, so now we still need to solve for time. This is very similar to that last problem that we were doing where we were solving for time. So let's go back and look at that formula here. Let's just kind of back up and see if we can't find that one. Where we did time was looking at our change in velocity divided by our acceleration. It really was twice the initial velocity when we did change in velocity. It ended up being 2 times, I'll just make a formula, 2 times the initial velocity in the y direction divided by the acceleration, and that gave us our time here. And this really was 2 times the initial velocity is equal to our change in velocity. So this is really delta v right here. So let's plug in some numbers to that real quick, and that will give us time. So time is 2 times our change in velocity, or 2 times the vertical velocity, I should say, initial vertical velocity. 2 times 180 divided by our acceleration, which was 10. And this really would end up being like a negative 180, and this would end up being a negative, hold on one second. So 2 times negative 180 divided by negative 10 meters per second squared. All right, so that would give us a negative 360 divided by negative 10, which would be a positive 36 seconds. Okay, there we go. All right, I'm going to do the next problems in a part 2 screencast, so go ahead and feel free to make sure you go to that next one.